Hi, in this video we will learn that there is a very nice characteristics for points at which a local max or mean for a function can occur. Well, this is so-called Fermat's theorem, and we will show some parts of the proof of that theorem too. Okay, let us start with the cases, like just see the geometrically, the graph wise. What is a local max for now? Okay, so it will be something like this happening, yes? Or it can be something like this. Well, we can go a little bit more. For example, it can be this point. Around that C, the function has maximum value at that point. Or we can have something like even these guys. Or this one even. All of these guys, when you look, you see a zoo of possibilities, different possibilities. But if you look very carefully, you notice that in all these examples I'm showing you here, all the last four of them, the function is not continuous or differential. In general, is not differentiable at that point x equal to c. And at the point, and on the first example where the function is differentiable at c, the tangent line is horizontal. In other words, f prime of c is equal to 0. Similar cases can happen for local mean, and this is what exactly the Fermat's theorem says. Says if function f has a local maximum value or minimum value at point C, then there are exactly two possibilities. Either f is not differentiable, or if it is differentiable, derivative of the function at that point is going to be equal to 0. So these are the only possibilities we can have. Either it's not differentiable or it is differentiable and the derivative is equal to 0. Just let's see a proof of the case where we have local max. So let's assume that f is differentiable at C and it has a local max at x equal to C. Well, means what? Means that there exists an interval such that f of c is bigger than all the values of function at any other point of this interval for all x in that interval, a be some interval. Okay. Well, being differentiable means what? F is differentiable means at c means that the limit exists. Yes, the limit of f of x minus f of c over x minus c as x goes to c exists. Well, since this exists, we can say that, okay, I can find the right limit of this guy, and left limit of this guy. So that was left limit, now this is right limit. And they need to be equal, yes, as x goes to c plus. If we get close to c enough, so we just work on this interval AB, we know that the value of the function is going to be always bigger than the value of any other point at AB. We are finding limits so we can restrict ourselves to the interval AB. This means what? This means that we are having a negative number in the numerator for all values of x in AB. And when we approach to c from the left, x minus c is going to be another, well, x is going to be a number less than c, so this guy is going to be another negative number. So when you multiply these numbers, so we are trying to find the limit of a function which is positive when we work on the interval, any left side of a c, so anything here. And when we look at the other one, positive one, this is going to be again a negative number, but since x is approaching to c from the right, this is going to be positive number. So we are finding limit of a function which is a negative on all the interval c to b. So we have right limit, limit of a positive, and left limit, limit of negative. So then this limit here, the function of the limit of the function from the left is going to be, which is what we know exists, and this is going to be a function, the value of the derivative of the function at c. Now we know that this guy is going to be a negative number. Here, on the other hand, we are going to have a positive number, well, bigger than equal to 0. Now, f prime of c, the right limit, left limit need to be equal to each other. So at some point it needs to be negative, at some point it needs to be positive. So this means that f prime at c is going to be equal to 0. And this is actually the complete proof for local max value. So the derivative either does not exist, but once it exists, it's differentiable function at that point, then the derivative function is going to be 0. Let me finish this video by a remark that the converse of the Fermat's theorem is not true. The converse of the Fermat's theorem is not true. What does converse mean? It means that, well, although this is what is saying, f has local max mean, then the derivative either does not exist or f prime is a 0 at that point. You cannot go backward. Then, and that means that there are points at which the function is not differentiable, or it is differentiable and derivative is 0, or f prime of c is equal to 0, but f has no local max mean value at those points. Fermat's theorem says that every point which gives us a local max mean will have these properties. It doesn't say the other way. It doesn't say that every point which has any of these two properties will give us a local max mean. It just provides us a list of points that we have to do a little bit more work to choose from which one gives us local max, local mean. For example, we can have examples actually. Example. Look at f of x equal to x cubed. This function is differentiable everywhere. F prime of x, which is 3x squared, at 0 vanishes, meaning that f prime at 0 is 0. But we did this example in another video. In the function f of x equal to x cubed doesn't have any local max mean. So f has no local max or local mean at all, and at 0 in particular. So has no local max mean at x equal to 0. As you can see, the derivative function at some point is 0, but that point is neither local max nor local mean. Okay? Or we can have another example. For example, f of x equals to half of x. Just an easy example when x is bigger than or equal to 0, or x when x is less than 0. Well, this function is differentiable. Let me write in black. Is differentiable everywhere but at x equal to 0. And indeed, we have f prime of x is half when x is strictly bigger than 0. At x less than 0, it is 1. At 0, it is not defined. So the point 0 has the property that the function is not differentiable. But if you look at the graph of the function, is, these are just lines, yes. So the graph of function goes like this. This is half, and then this is x. Yes. So as you can see, the function has no local max mean at all. So f has no local max mean value at all, in particular at x equal to 0. What does this say? It says that, well, we need to do a little bit more work. Fermat's theorem just gives us a candidate of points which we can work a little bit more and figure out which one gives us a local max and local min. It doesn't give us the whole points at which we have local max min. It just gives us some characteristics, not all the characteristics. Some characteristics, we can pick these points, we will have a list of points, and then there will be other tools called first derivative test, second derivative test. We have to use those ones, more information to figure out which one of these guys give us local max or which one give us local